All right, these are the notes that you need to have down to really understand what an empirical formula is. So first off, if I had table salt, I think most of you in this class would probably recognize that table salt has a common chemical formula of NaCl. And what that means is there's one sodium for every chlorine. Chemists are lazy, we don't write ones. If I wrote Na2Cl5, that wouldn't make much sense to you. And that's because that's not the correct formula for table salt, particularly sodium chloride. And if I wrote Na3Cl2, that wouldn't make much sense either. Both of these are incorrect. We call these typically a chemical formula. These are the incorrect chemical formulas for sodium chloride. This is the correct formula. The reason why it's correct, which I'm going to label right here, it is correct because it represents the actual ratio of Na to Cl. And that ratio is 1 to 1. We just don't write 1 to 1. I'll give you an example of something else that's pretty familiar to you, that you know what the ratio is. How about carbon dioxide? Everyone in this class knows that carbon dioxide is C to 2 oxygens, right? Well, in these notes about empirical formula, what an empirical formula is it's the lowest ratio between the atoms bonding together. So we know CO2 is correct. You guys know H2O is correct. Let's go back to the NaCl example one more time. Those are examples, again, of the lowest appropriate correct ratio of how many atoms are bonding together. In this case, it would be 1 carbon, 2 oxygens, 2 hydrogens, 1 oxygen. So going back to the NaCl example, let's write down Na6Cl6. Believe it or not, that's the correct ratio. Notice that there's a chlorine for every sodium. That's why it's the correct ratio. But it's not the lowest common ratio possible for this. The lowest ratio would be NaCl, which is what you're used to seeing. You could think of it this way. You can divide and multiply ratios. I could divide both of these by 6. What I do to one, I have to do the other, just like you have in your rules for algebra, and I end up with NaCl. Does anyone in this class have a question about that? So this right here is what we call the empirical formula, because it is, in particular, the lowest ratio. Do you guys have any questions about that? All right, now we're going to transition to how we collect data for the lowest ratio in a lab like the one you're going to be doing. The lab you're going to be doing requires you to figure out the ratio between magnesium and oxygen. So for magnesium and oxygen, you don't know what the ratio is. So I'm going to put X and I'm going to put Y because those are unknowns. That's what we got to figure out. So the only way we can figure out the empirical formula is by, of course, measuring how much of each we have. In this lab, you have a crucible. It's like a little clay pot like this, and it's got like a little lid, a little handle. There's your crucible. And you're going to start by putting magnesium in the bottom of the crucible. Then you're going to heat it with a lot of heat energy from a Bunsen burner. What that does is it increases the kinetic energy in your crucible to the point where magnesium has enough energy to start reacting with things around it. Well, what's around it? Particularly air. And what's in air? Well, about 77% nitrogen, about 20% oxygen. It's actually mostly going to react with the oxygen. So the oxygen is going to come in here and bond with the magnesium. Then afterwards, after it's reacted with the air for a while, you're going to have a crucible that's made primarily of magnesium and oxygen bonding together. Class, do you have any questions about this? Say that out loud. Say it really loud.
Is it 20 or 70% oxygen?
About 20%. So now, imagining I was measuring the mass of the magnesium before, and then I'm measuring the mass of this afterwards. That would essentially be my product, what was produced at the end of this, okay? So I would do this. I take my crucible with MgO XY, and I could actually subtract it from my crucible with the original amount was just magnesium. And if I do that, I'm left with just oxygen. So all you need to know is the mass of the product and the mass of what you started with. You do some subtraction, and then you know exactly the amount of magnesium you started with in grams and the amount of oxygen that bonded to it, because the mass is going to increase because oxygen's bonding to the magnesium. This is the way that I get that data, and I'm putting boxes around the data that you need in this lab to answer the question. Now, for an empirical formula calculation, what you do is, let's use some example data. Say we measured out 2.6 grams of magnesium, and what bonded to it was 1.3 grams of oxygen. That's after we finish the lab. Well, we can't figure out the ratio from just the grams. We have to actually convert it into moles, because moles is how many. How heavy doesn't tell us a ratio, because magnesium does not weigh the same as oxygen. I can't compare the ratio in terms of grams. I have to compare it in terms of amounts of stuff. So the molar mass of magnesium is 24.31. For oxygen, it's 16. And then I just go into my calculator here, and 2.6 divided by 24.31, and I end up with a number of moles which, rounded to the correct number of sig figs, ends up being 0.11 moles of magnesium. And then I do the same for oxygen. I take my 1.3 grams and divide it by 16 grams per mole. And again, keeping it to 2 sig figs, I get 0.081 moles of oxygen. So now, what I'm going to do is I have this ratio. Well, that ratio doesn't make a whole lot of sense. I can't write out a chemical formula, an empirical formula specifically, like this. I've never seen that. That doesn't make any sense. So we have to simplify this ratio. The way we simplify the ratio is we take both of these numbers and we divide it by the smallest amount. 0.11 is larger than 0.081. So I'm going to divide each of these numbers by 0.081. When I do that, I get magnesium at a ratio of, let's see here, 0.11 divided by 0.081 ends up being probably a pretty big, or pretty small number. It's 0.135.
Yeah, divide by 0.81.
Did I not? Oh, you're right. I totally divided by the wrong thing. So magnesium in this case would be 0.11 divided by 0.081. And then I get 1.35 for magnesium. And then I get, for oxygen, I have 1. Okay, now that still doesn't work for a chemical formula. That's still not an empirical formula because I wouldn't write this out. That doesn't make sense, and besides, we don't write ones, we're lazy in chemistry. So what I have to think to myself is I have to go, all right, I've got this ratio, but I need to make sure I have numbers that are not decimals. What can I multiply both of these to preserve the ratio and then end up with numbers that aren't decimals? So if I see a 0.3, I know that I can multiply it by 3, and it pretty much becomes, you get rid of the decimal. It's like, this is a third. I can multiply that by a 3, and then I simplify that. So I can multiply both of these by 3, and what I'll get is Mg4O3. And that would be my empirical formula. That's the lowest ratio possible. Now, let's just say, for example, what if you accidentally messed up and you got Mg12O9? Believe it or not, the one on the right is the same ratio as the one on the left. The difference is this is the empirical formula. The other one is not, because it's not the lowest ratio possible. Could someone raise their hand and tell me what I could divide this by to get a better ratio? 3. Yeah, Heath. 3. So I could divide both of these by 3, and then I end up with exactly that. Do you guys have any questions about that? We're not done. Hang on. One more part to this. Last part to this that we need to understand when it comes to empirical formulas is we should be able to make a prediction about an empirical formula based on the periodic table. That's the point of us doing this lab at this time of year. We've got magnesium here on the periodic table, we've got oxygen there. This is a really cheap periodic table, but there's my division line. I know this is a metal. Now metals like to lose electrons typically, and non-metals typically like to gain electrons. We've learned that elements on the periodic table like to look like a noble gas. That's the most stable electron configuration. So I can look here at my periodic table that I'm getting out right here. Magnesium's right here. Now, magnesium has a choice. It can either gain 1, 2, 3, 4, 5, 6 electrons look like argon, or lose 2. It's probably going to lose 2 electrons to look like neon. That's easier. Wait up. Oxygen is most likely going to gain 2 electrons. This is the essential information you need to have down before you begin this lab tomorrow. Are there any other questions, folks? You're dismissed.